Hey everyone, welcome back, and today let's solve Leetcode problem 1780, titled Check if number is a sum of powers of 3. So we're given an integer n, and we need to simply return true if it is possible to represent that integer input n as the sum of distinct powers of 3, meaning we're not allowed to reuse any duplicate or reused powers of 3. And if that's not true, hence otherwise, we'd return false if we can't actually represent n as the sum of unique powers of 3. And an integer y is defined to be a power of 3 if there exists an integer x such that 3 to that x power is equal to y, meaning really just giving us the definition of what a power of 3 really is, 3 to the power of some integer x. So in example 1, we have our input n to be 12, and in this case, we actually output true. Now, the reason why we output true is because we can actually represent 12 in a way of distinct powers of 3, more specifically, the sum of those distinct powers of 3, right? We could have 3 plus 9. 3 is a power of 3, and so is 9. And last time I checked, 3 plus 9 was equal to 12, and so that is a valid approach. In example 2, we have n to be 91, and it's still completely valid because we can do 3 to the 0th power plus 3 to the 2nd power plus 3 to the 4th power. Something very important to note, 3 to the 0th power is not 1, or rather, 3 to the 0th power is not 0 or undefined or 3, it's actually 1. And that kind of brings us to another very important formula to keep track of. Anything to the power of 0 is always going to be 1. In reality, we're using the powers 0, 2, and 4, so that would be 3 to the 0 plus 3 to the 2 plus 2 to the 4, or 1 plus 9, or rather 1 plus 9 plus 81. And if you sum up those values, you would get 91, and so this is a true output because both 1, 9, and 81 are all powers of 3. In example 3, however, we have n to be 21, and there is no way or combination of powers of 3 that we could sum up that without reusing any powers of 3 to actually get a value of 21. And so we're going to have an output of false for this case. So for the constraints here, we say that our input integer n is going to be at most 10 to the 7th power. And yeah, that's about it. So that kind of leads us to the very important observation to really make. And I think this is a very simple problem, at least relatively, that a lot of people would probably really overthink, at least in terms of code. And once you actually get the logic, the code isn't actually too bad at all. And that kind of brings us to that main observation that we really need to make in the problem to really solve it efficiently, right? Now, on a high-level rundown, how does this problem really work? Basically, it's similar to kind of representing a number in base 3 when we're actually checking to sum up distinct powers of 3. We're trying to represent a number in that base 3 kind of method or formula, right? So if we express, let's say, our input integer n in base 3, we know that each digit, it should either be a 0 or it should be a 1 to always make sure that we have a sum of distinct powers or rather unique powers of 3. And if any digit in that base 3 representation is 2 or greater, we know for a fact that n cannot be formed to actually use those distinct powers of 3. So really, how is our solution going to work? Basically, we can really solve this problem by just repeatedly checking if n is actually divisible by 3, and we always have to make sure at each iteration that we divide n by 3, it's either the remainder of n divided by 3, either it's going to be 0, meaning it is divisible by 3 perfectly, or it has a remainder of 1. That's fine. But if we get a remainder of 2 at any point in time when we divide n by 3, we know we have to return false, because if any digit, in fact, in the base 3 representation of n is actually 2 or greater, we know that n cannot be formed using distinct powers of 3, and so we have to immediately return false if we have a remainder that's greater than 1, meaning it's equal to 2, right? If it's 0 or 1, that's perfectly fine. So yeah, that kind of leads us to the high-level rundown. Very straightforward solution here and implementation. Basically, while n is actually greater than 0, so while we actually have a non-zero, non-negative valid n value, we're going to first compute n modded by 3 or n remainded by 3 using the modulus operator. That's going to give us the last digit in base 3 at this current iteration. And if that current remainder after we computed it in each iteration, if it's 2, we know we have to return false immediately. Otherwise, if it's not 2, if it's 0 or 1, we can simply just continue by dividing n by 3 with integer division and moving on to the next iteration. And if we finish the loop at all, or rather if we finish the entire loop without at all encountering 2, we know that this can actually be formed in base 3 representation without any duplicate or distinct powers of 3, and we can actually return true. But otherwise, we have to return false in the loop itself if we ever get a remainder of 2. So that brings us to the solution that we go in. So, like we just talked about, while n is greater than 0, so while n is actually valid to still do operations on, while we can still process n until it becomes 0, and this is basically where we check every single digit in its base 3 representation, in n's base 3 representation. So while n is not null, while we can still process it, let's actually calculate the current remainder of the current value of n. And it would be n modded by 3. This percentage symbol in Python is simply the modulus operator. It's going to be n modded by 3. And that remainder is basically being used to actually extract the last digit in the base 3 representation of n, right? Now, in this current iteration, of course, whatever value it is. Now, if the remainder that we just calculated, if it's equal to 2, we know for a fact, okay, we already found a false n. We have to immediately return false, because we know if it is actually equal to 2, then n cannot be formed using distinct powers of 3. We have a remainder that's not 0 or 1. We have a remainder of 2, and so we have to return false. However, if we haven't returned false yet, we didn't have a remainder of 2, but rather we had a remainder of 0 or 1, we can actually integer divide n by 3. So the way we can do that in Python, a little bit simpler, is basically just dividing n by 3, and yeah. Right, so basically what we're really doing here, the main chunk or logic of this solution, if the remainder isn't 2, we haven't already returned false, we simply then proceed in the current iteration by then dividing n by 3, and these two double slashes here in Python simply mean integer division, right? And what this is really doing, like the operation that this really is performing, is that basically we're removing the last base 3 digit from the n representation, or from n as a whole, and then we can actually check the next last base 3 digit in the next iteration when we divide n by 3 again, right? And effectively, once this loop is actually done terminating, or done executing once it terminates, if we haven't returned false at all with any of the remainders in any iteration of this while loop here, once we've processed n completely, we can return true at the, or after the for loop finishes, after the while loop finishes, because if we haven't returned false already, that means we finished the loop without finding a 2, and that also means a remainder of 2, that is, and that also means that all the digits in the base 3 representation were either 0 or 1, and so we can return true. So if I were to submit this, this would actually be an accepted solution, and this would be a valid approach, and as you can see, this really is just about as efficient as you can get it to be. So now let's go ahead and kind of talk about how this code actually works as a whole real quick. Another quick high-level rundown. Basically, we're checking, okay, can n be represented as a sum, keyword here, of distinct or unique powers of 3? When we're doing this, we're actually converting n into base 3, or into its base 3 representation. Now, if n only has zeros and ones in each digit in its base 3 representation, we know it's valid. Otherwise, if we see a 2 for any remainder or any digit in the base 3 representation of n, we have to immediately return false. And we can simply kind of simulate this using a very simple while loop here, and repeatedly dividing in each iteration n by 3, and that always makes sure that all the remainders are acceptable, meaning they're 0 or 1. Right, that's really the main chunk of logic that we really need to understand here, right? We're basically representing this number n in base 3 representation, right? And we know if we want to express n in base 3, every single digit has to be either 0 or it has to be either 1, because we want to ensure a sum of distinct powers. Otherwise, we'd not be using distinct powers if we had a remainder or digit that's greater than 1, meaning it would be equal to 2 in the context of this problem, right? So what is the runtime complexity of this solution? This is actually going to be big O of log base 3 to the n. Right? Why is this? Well, because we're very simply just repeatedly dividing n by 3. It's very similar to a binary search approach where we're dividing the array by half each time, dividing it by 2, if you will. And so instead of log base 2 of n, this would be big O of log base 3 of n, because we're repeatedly dividing n by 3 instead of 2. Right? And since n also does decrease exponentially, the number of iterations is still small, is relatively as well, and so this is still a very efficient approach. And the memory or space complexity, as you may have imagined, we're not even using any other auxiliary memory or any extra data structures. Really, we're just dividing n by 3 and calculating an integer remainder. That's going to be a constant time integer because we're really just using that integer variable and nothing else, no additional data structures. And so this is actually a constant time or big O of 1 memory complexity. So if you guys enjoyed the solution and learned something new, please consider liking this video and subscribing to my channel. And without further ado, I will see you guys in the next video. Bye-bye.